Okay, hello everyone. You should be able to hear me now. Um, just give me a thumbs up if you can see the slides and you can hear me. Okay, excellent, perfect. So what we're gonna do today is continue where we left off on Wednesday, which was rolling without slipping in the angular momentum chapter. We're going to apply that today just to rolling with slipping, just because, you know, that's a natural extension of that problem. And then we're going to go into actual angular momentum and conservation of angular momentum, and sketching sort of the parallels between angular momentum and linear momentum. Of course, it will not surprise you that, again, there are parallels between the angular and the translational motion. So we're going to start with rolling without slipping. That's what we looked at last time. So that's the example of a any wheel, bicycle wheel, for example, that's rolling on the ground, and where the point of contact with the ground is not slipping, or where the wheel is not slipping, and that means that the point of contact with the ground has to have a zero velocity, right? So let me put this there. Okay. So if there's no point of if there's no velocity in the point of contact, that means we can actually write this in terms of I think, let's see, yeah. So we use this figure here. We can write the velocity of the point of contact in terms of the motion of the center of mass of the wheel and the motion of the point on the wheel that is rotating in the center of mass. And so what we used last time was in rolling without slipping, and we applied this for an inclined plane, but these are general statements. So for rolling without slipping, we have that this contact point is not moving. So the contact point is not moving with respect to the ground. And from that, we then derived that there's a connection between the center of mass acceleration and the angular acceleration. So that's one thing we did for rolling without slipping. The other thing we did is, since we have rolling without slipping, since the velocity of the contact point is zero, we're in the case with static friction. And if we have static friction, then the force of static friction is as large as it needs to be, as large as needed to maintain that static situation. And this one we solved from the angular equation, Newton's second law equations. We solved this from tau is so the torque, which is caused only by the force of friction. So that was I times the angular acceleration. And if we put all of that together, then we found that ultimately we end up with an with a linear acceleration, which we derived last time. That was mg sine theta over m plus, and then we have our moment of inertia that plays a role, of course, over r squared. And that was related directly to the angular acceleration a. So that's what we did last time. So just to remind you, we started from the fact that the contact point is not moving. That allows us to calculate the connection between the angular and the linear acceleration. And then we used static friction, which allowed us to then ultimately get to the answer by determining the value for static friction. So now we're going to do the same thing. I'm going to put it on the side here. Now we're going to do rolling with slipping. So in rolling with slipping, there's a couple of differences. Obviously, otherwise I wouldn't be covering it separately. So if we go back to the slides here, so now in rolling with slipping, these are, you know, these are exactly the same figures. The only thing that's changed here is without this turned into with, and the forces are changed a little bit. So this is without slipping. So you see that here we have the force of static friction at the contact point between the wheel and the slope. If we now go to the situation with slipping, then you see the force that's applying here now is the force of kinetic friction, because now this contact point is not stationary. Now this contact point is sliding on the inclined plane. So now there's kinetic friction that's playing a role here. Everything else is the same. The normal forces, mg sine theta, mg cosine theta, none of that has changed. The only thing that has changed is the force of friction. So if we go to our whiteboard here, so we have that Vp is not equal to 0. So the contact point is not stationary. The contact point is moving. And since it's moving, that also means that ACM won't be equal to R times alpha. So we can't use that equation as input. But we have a second path here. We have, instead of static friction, we now have kinetic friction. And of course, I present these as separate, but of course, the reason why we have static friction here is because Vp is 0. And the reason why we have kinetic friction here is because Vp is non-zero. And in kinetic friction, we don't just have to solve for Fs, the static friction. So really what we did here was solve for Fs from that equation, from the Newton's second law. Here we can, we know Fk is going to be equal to mk times the normal force. So we know that this is true. We don't need to solve for the force of friction. So while we lose one equation that we could use to solve this problem with, we gain another one. We gain the fact that we know that the force of kinetic friction has to have a certain value. And so if we look at this, so we have mu k times the normal force. The normal force we can derive from the equations in the y direction. So this is the y direction here. So the normal force is going to be equal in magnitude to the force of the weight, of the force of gravity along the y direction. So the normal force will be equal to mg times cosine theta. And that is because there's of course only acceleration along the slope. There's no acceleration in the y direction. So this is mu k mg cosine theta. That's our force of kinetic friction. So this is from our Newton's second law. This is what we get from the y component. We can write down the x component as well. So if we write down the x component, we'll get that mg sine theta minus fk will have to be the total acceleration, the linear acceleration of the center of mass down the slope. So fk, which we, or let's start with the other term, mg sine theta. So that's the component of the weight that's along the direction of x. And then minus force of friction, which we now know, that's mu k mg cosine theta. That will have to be equal to m times a cm. So that's our x component equation from Newton's second law. These are Newton's second law equations in translational motion or translational coordinates. And of course we'll have one in rotational coordinates too. So I'm going to call that tau. So this one is going to be similar to the one we used in the case of rolling without slipping. So the only torque will be from the force of friction. Again, that's the only force that doesn't apply at the center of rotation itself. So that's the only force that will result in a non-zero torque. And the magnitude of the torque will be the distance to the point where the force applies times the perpendicular component of the force to the lever arm, and that's the entire force here. So it's going to be R times Fk. So Fk times R will have to be, so that's the torque, that will have to be equal to the moment of inertia times the angular acceleration. So what we did in the first problem, in rolling without slipping, is that we used the equations that we had and we solved them for the acceleration A of the center of mass. So now we have a different set of 3 equations which we can solve for the acceleration of the center of mass. In fact, we can solve based on just the second equation, since we've already substituted the first equation into the second equation. We can immediately solve for ACM, and that's going to be this, from this equation, that will be G times sine theta minus mu k times G times cosine theta. So that's the linear acceleration in the case of rolling with slipping. And in the case of rolling without slipping, we could immediately correlate that, or use that to determine the angular acceleration. Now here we have a little bit more work to do for that. For that we will need to use the third equation here. So alpha, the angular acceleration, will be Fk. I don't know what's wrong with my F's and K's today. Fk R over I Cm, or if we plug in the value for Fk, that will be mu k R m G cosine theta divided by I Cm. So just to kind of look at that again, so the differences between rolling without slipping and rolling with slipping are related to the contact point. That, of course, in the case of rolling without slipping, has a 0 velocity relative to the ground, or relative to the object, the slope that it's rolling on. And that then causes the differences in static and kinetic friction, and it causes some different equations and ultimately different results, right? So that's what we get in this case. Okay. So that's the difference between rolling with slipping and rolling without slipping. And again, one of the reasons to use this problem and to go in a little bit of depth is that it actually fits well as an example of combining translational and rotational motion, angular and linear motion, and which we covered, for which we covered the angular motion part in the previous chapter. Now you might remember that we actually solved the problem of objects sliding down an inclined plane without slipping, i.e. frictionless objects, or with slipping, when there's some friction that occurs and there's therefore some energy loss. We used energy conservation for that. So we can, of course, use that here as well. Okay, I don't have any slides for that. So we can use energy conservation to solve these kind of problems as well. So let's use energy conservation, or energy considerations to solve this kind of problems. And we'll start from writing down the total mechanical energy in a system. And that will consist of the kinetic energy of translation, so 1/2 mv center of mass squared, plus the total energy of rotation, 1/2 m, no, not m, 1/2 I, the moment of inertia around the center of mass times omega squared. So that's the rotational energy. And then there will be potential energy. And in our case, in particular for this problem of an inclined plane, that will be mg times the height. And now we can use this to solve certain kinds of problems, right? Let's imagine that the problem is that at the top of an inclined plane, we start start from rest. So if we start from rest now, in this case, this will mean that the center of mass velocity is 0, and the initial rotational or angular velocity is equal to 0. So that means that at the top of an inclined plane, the energy, the total energy, will be equal to just potential energy mg times h. And actually, one of the things I'll do is I'll compare the energy at the top of the inclined plane with the energy at the bottom of the inclined plane, so the height can be related to the distance along the inclined plane. Let's call this distance d. So I'm going to make a little drawing here. So we're going to call this the height. This is theta. And we'll call this the distance d. And if that's the distance d, then the height is, of course, d times sine theta. So we're going to write this also as mg times d sine theta. So that's the total energy at the top of the plane. So we've sometimes called this condition A, and then B will be at the bottom, at the base of the inclined plane. So now we're not at rest anymore, but we have a zero gravitational potential energy. So at this point, the energy, the total mechanical energy, so here this was AEA, this is EB, will now be 1/2 mv center of mass squared plus 1/2 I center of mass omega squared plus 0, because we're at that point at zero potential energy. So now again, we can split up our situation into rolling without slipping and then rolling with slipping. Rolling with slipping. So what we're going to do is we're going to, of course, say that the change in total energy has to be equal to the work done by external forces on this object, and this is the work done by dissipative forces, since we already include through the potential energy the work done by the gravitational force. So in the case of rolling without slipping, we can use that the center of mass velocity will be r times the angular velocity, and if we then look at the equation that we have there, we have that this is equal to 0 because there are no dissipative forces that are causing energy to be lost, because all of the dissipative forces, the force the force of friction is static friction, and we know that static friction doesn't correspond with a displacement. So if there's no displacement along that force of static friction, then it will not correspond to any loss of energy. So in rolling without slipping, we set this dissipative energy loss equal to 0 because there is no dissipative energy loss. That's of course exactly why we use rolling without slipping, because it is something that allows us to conserve energy rather than rolling with slipping or essentially dragging things on a surface. That's of course where the friction losses happen. So that's why this is the reason why people invent the wheel and keep reinventing the wheel. So in this case, or EA will have to be equal to EB, and that means that mgd sine theta will have to be equal to 1/2 m times VCM squared plus 1/2 ICM. And now omega I'm going to write as VCM over R squared. And you can see that we can solve for the velocity. We could have done this differently, and we could have solved for omega from this equation. But we can write an expression for the velocity, and unfortunately it doesn't fit on this page. But we can write VCM will be the square root of 2 mgd sine theta divided by m plus ICM over R squared. Something like this, right? So that's one way in which we can use energy considerations to determine the velocity at the base of the plane in the case of rolling without slipping. So now let's look at the other case here, rolling with slipping. So in this case, we'll have that the change in energy, the total kinetic energy, is equal to the work done by the dissipative forces. And this actually will be non-zero. In this case, it's non-zero because we have slipping. So there is force times displacement that's non-zero. Force of kinetic friction will correspond with a dissipative work that is being done. So this is going to be equal to, and I actually wrote it as Fk times d is non-equal to 0. It will in fact be exactly Fk times d, with the d as defined here. So over the entire length of this slope, there is a force of friction Fk, which is constant because it only depends on the normal force. Fk will be equal to minus mu k, will be equal to mu k times n. Yeah, I'm gonna keep the minus sign there. There, minus mu k, since we picked our x direction in the opposite direction. So the work done by that dissipative force is Fk times d. And so that means there will be an energy loss, and EA will be equal to EB plus that, I guess it's EB. I guess it doesn't really matter how we write it, but EA will be equal to EB plus the dissipative energy loss. I think technically I should have a minus sign here. And so that will mean that if we now plug in our values for EA, so we have mgd sine theta is equal to EB will be 1/2 mv center of mass squared plus 1/2 ICM and omega squared plus Fk times the distance. Now, unfortunately, this is how far we can go with rolling without slipping using just energy considerations, and the reason is that we cannot actually rely on this equation. We cannot rely on the fact that there's a connection between the center of mass linear velocity and the angular velocity at all times. So at the time we're at the bottom of the inclined plane, the center of mass velocity and the angular velocity will not necessarily be related, or they won't be related by a single formula like this. So this is unfortunately as far as we can get, and so this is in some sense indicating what the limitations are of the energy approach, which we can use in the case of rolling without slipping. So keep that in mind. Typically, the problems where you'll want to use this is going to be therefore problems of zero energy dissipation and problems in rolling without slipping. Okay, so we'll probably at the very end of class today come back to another example of energy conservation in the case of angular momentum, which brings me to indeed angular momentum. So finally, after almost 2 lectures in the angular momentum chapter, we are actually going to introduce angular momentum. So remember that we've made a number of connections now between angular motion and linear motion. And one of them looked something like this, or displacement vector along the tangential coordinate was the angle cross r, or we wrote omega is v cross r. Sorry, I'm writing this the wrong way around here. It's v, that's omega cross r. And the acceleration, the tangential acceleration, was the angular acceleration cross r. We've introduced the torque, which was r cross f, right? So you can see that all of these things where we take a cross product with r, that's going to be a hallmark sign of moving from linear to angular motion. And so we're going to use that now to define the angular momentum of a single particle. So for a single particle, the angular momentum is defined as L, little l, and this is sort of a script L is often used because in print a lowercase l looks very much like an I in some fonts, so that's often avoided. So that's why you'll see this either as a script L or in some other way made clear that it's an angular momentum. So that's going to be r cross p, where p is the linear momentum. So that's the definition of angular momentum, the quantity angular momentum, and you'll see it's, since it's r cross p, it will be perpendicular to both the position and the linear momentum vector. And of course this is going to be the counterpoint to linear momentum will be angular momentum, just like the counterpoint to angular velocity is linear velocity, and so on. So if we go to an example here, so if we have a point that is moving with a momentum, a linear momentum vector p in this direction, and it's moving at a position r away from the origin, then we can calculate the angular momentum around the origin by using a right-hand rule and taking the cross product here, and that will give us, using the right-hand rule, an angular momentum that is pointing out of the plane here along the z direction. Since it is a vector product here, a cross product, the magnitude will be r times p times sine theta, with theta is the angle between r and p, right? We can also write this as r perpendicular times p, or we can write it as r times p perpendicular. So think back on our discussion of torque. So r perpendicular is r projected on p, and p perpendicular is r perpendicular is not r projected on p. R perpendicular is the component of r perpendicular to p, and p perpendicular is of course the component of p perpendicular to r. So if we go back to the slide here, the perpendicular components are, in this case, r perpendicular is the perpendicular component of r perpendicular to the momentum, and we could have drawn here a component of the momentum that's perpendicular to the direction of the vector r. So that allows us to think about this angular momentum also in terms of, you know, lever arm and line of action, if you wish, except we don't call it line of action when it's about the momentum, but we can think of this as the distance from the origin to the line of action, the perpendicular distance to the vector p, and we can think of p perpendicular as the perpendicular component, just like we use the perpendicular component of the force in our calculation of the torque. Now, if we introduce something like this, an angular momentum, we don't do this because it's useless. So we're going to do something useful with this, and then what we're going to do is we're going to relate this back to Newton's second law equation. So we're going to take the time derivative of the angular momentum, and so we're just going to use chain rule here. So if we take dl dt, that will be dr dt cross p plus r cross dp dt, right? Now let's look at this first term here, dr dt, that's v, right? And the momentum, we know that that's m times v, the linear momentum. And then here we have r cross, and dp dt, you might remember that we wrote Newton's second law as F is dp dt, which is really just m times a, right? So r cross dp dt is actually r cross F. So now we have here the cross product between two parallel vectors. They're actually a scalar times the cross product between two identical vectors. So this will be 0. So the only thing we're left with is r cross F. But remember what r cross F was. We actually wrote it here as well. That's the torque. So r cross F is the torque. So dl dt, the time derivative of the angular momentum, is equal to the torque. And of course that is, so I should probably be a little bit more specific here. So if we wrote our Newton's second law here, this was actually the total force. So this is the total force. So if we end up here with tau, the torque, this is the total torque from all forces that apply to this particle. But what it results in is essentially that in addition to our dp dt is equal to the total, the net force on a particle, then dl dt will be equal to the total torque on a particle. And so again, we have something here in translational motion, and we have an expression here in angular motion, rotational, I guess I should call it. If I call it translational, with that goes rotational. If I call it linear, then this is angular, just to keep my terms straight. So that's the connection between angular momentum L, again defined as r cross p, and the torque, again defined as r cross the force. This was for a single particle. For multiple particles, we can of course define a total angular momentum, and that's what we're going to call capital L. So that's the sum over I of little li's. And what we'll find is that dl dt for multiple particles will be the total, the net external torque on that set of particles. So if we have multiple particles, they may be applying torque. They may be applying forces to each other, but those are not the forces that we include. There may be torques on these particles due to each other, but those are not external. So the only torques are the external torques on these particles that we include, and that gives us then an expression for the change in the total angular momentum of all of those particles, where this one might have Li, L1, L2, and L3. So we have this for one particle, for multiple particles. The other thing that will be relevant is using this to calculate the angular momentum for rigid bodies, for extended objects. Before we go to that, let's see, angular momentum of a particle. So there's a problem-solving strategy again here. Usually, this is going to be very similar to the kind of questions that we get about Newton's second law in general. So you'll want to do the same thing that we've done for all of these angular motion problems. So choose a coordinate system around which to calculate the angular momentum, write down the radius vector, write down the momentum vector in that coordinate system, and then calculate the angular momentum, and then write this in terms of the torque, right? So let's skip this one. So for rigid bodies, we're going to essentially approach this again as a collection of many particles that allow us to either take the sum or to turn the sum into an integral and take the integral. So for example, here in this object, I don't know, it might look like a top. There's a little volume element that has a mass delta m here. It's at a distance ri away from the axis. And if it's at a distance ri away from the axis, we know that it moves at a velocity that is ri times omega. And all of the objects, all of the points in this entire objects move with that same angular velocity omega. So the only thing that will determine their velocity at a certain distance r from the axis is r times that omega. So we can use that now to calculate the total angular momentum of this object. So for a rigid body, L will be, now it's not going to be the sum over all little l's, but it's going to be the integral for, let me not write dm there, let me write dv. So it will be the integral over the entire volume of the angular momentum for infinitesimal volume elements. And so we're going to write this as the integral over the entire volume of r cross, and the part that is going to be in the place of the momentum, the linear momentum here, is v dm. That's the delta p, the infinitesimal momentum, or I guess I should write it as dp. That's the infinitesimal momentum contribution, which unfortunately, for mathematical reasons, we now have to put into that cross product. If we pick our coordinate system with the z-axis along the axis of rotation, which is what we've done in this drawing here, if we pick our z-axis along the axis of rotation, then then r will be perpendicular to the axis of rotation. V will be in the plane, in the xy plane. So r will be here. V will be in the xy plane, and ultimately we'll end up with an angular momentum that depends only on that is in the direction of the z-axis, and that has a magnitude that is given by the integral of r times v, which is r omega dm over the entire volume. Because omega is constant, we can bring that out out front, so we get z times omega, and then we get the integral of r squared dm. And now you might remember that this is exactly the expression for the moment of inertia. So this becomes I times omega in the z direction, or if we put this in an easier form, L, or if we summarize this, L is going to be I times omega for rigid bodies. So for rigid bodies around an axis, the moment of inertia around a certain axis times the rotational, the angular velocity around that axis will give us the angular momentum of that body around that axis. And of course, the same thing is still true as before, that dl dt will be equal to the net force, the net external force, net external torque on those rigid objects. Okay, so just to recap that last part. So our angular momentum is defined as r cross p dl dt is equal to the torque, and for rigid bodies, L, the total angular momentum, is I times omega, and in this case let me not write this as a vector. So those are the important formulas on angular momentum, and what we'll come back to on Monday is now how to use conservation of angular momentum. You might remember we talked about conservation of momentum, so there will be conservation of angular momentum. Conservation of momentum will essentially be what we already covered was conservation of linear momentum. So now there's going to be conservation of angular momentum, and then we can start to do things like the collisions, which we treated in linear momentum problems. We can sort of find equivalents in angular momentum problems. So more about that on Monday. So have a good weekend, and talk to you all on Monday.